Hi everyone. Before we start, I have two announcements. The first one is that the head of the school has asked us to um, fill in the academic service. Okay, so if you can spare a few minutes when you have the time, please fill in the academic survey. Okay, and the second announcement is that the next lecture on Friday will be live through Microsoft Teams. Okay, I'm going to solve some of the exercises on the worksheet that I have published on the virtual campus. So it will be live for you to be able to ask questions or to choose between the different exercises if you are interested in a particular one. Okay, so instead of recorded or pre-recorded session, we will have a live lecture, and I will send you an invitation through Microsoft Teams. Okay, for this Friday, sorry, at 11 a.m. Okay. So today we are going to focus on this lecture on binary trees. In the last lecture, we defined what we call trees, the type of graph that we call trees, and we studied different notions related to trees. And one of them was the arity of the tree. And you may remember that the arity of a tree is the maximum of the number of children that a node can have. Okay, so if the node that has more children has, for instance, 5, then we say that the graph, the tree is a 5RE tree. Okay. One type of tree that is very common and very useful is what we call a binary tree, which is a tree in which each node has at most 2 children. Okay. And as you will see, this can be used, for instance, to represent arithmetical expressions and then to evaluate those arithmetic expressions. And that is what we are going to study today. Okay, so the formal definition of a binary tree is a set of nodes in which each node is either empty, which is a trivial case, or has a root node and then another tree, which is the left subtree, and another binary tree, which is the right subtree. So this is kind of a, well, it's a recursive definition, but it's also kind of a definition of a class in a programming language. So you could have something like class binary tree, and then you can have, for instance, a node that is whatever type of element that you store in the tree, for instance, an integer, and then you have the left tree, which is a binary tree, and the right tree, which is also a binary tree. Okay, so it's a recursive definition of a data type, okay, in which inside the data type we refer to the class. Okay, so we have a recursive class, a recursive type definition. This is very useful, and you will use this kind of definition and this kind of structure in other courses, for instance, in courses in algorithmics or data structures. Okay, so let me give you an example of this kind of graph, of this kind of binary tree, and we have here in the figure this kind of situation, this kind of graph, in which you see that each node has a left subtree and a right subtree. Okay, and it is important to notice that it's not the same to be the left subtree and the right subtree. Up to this moment, we always stated that in a graph, the only thing that is important is what element is connected to what. But in the case of binary trees, we impose a little bit more structure. So for instance, here, H is the right child or the right subtree of D, but the uh, left subtree in this case is empty. Okay, so you must take into account that it is different to be the left subtree or the right subtree, and this will be important, for instance, for the kind of tree traversals that we are going to study in this lecture. Okay, so a few considerations are in place. The first thing is that notice, and this is very important, that a binary tree may be empty. Okay, this is important because in the definition, in the recursive definition, we need some way to stop. If each tree contains a left subtree and a right subtree, and none of these trees are empty, then we have an infinite structure. Okay, we do not stop. So we need a base case, and the base case is the empty or null tree. Okay, and also we keep the names, the kind of notions that we studied in the previous lecture, and we say that the the root node of the left subtree is the left child of the root, and the same is said about the right subtree and the right root. Okay, so for instance here we have that F is the left child of C, G is the right child of C. Okay, I think this is easy to understand. Okay, so why are we interested in binary trees? As you will see, binary trees are important for storing information and storing this information in a particular way, in a structured way. So we can later access this information in ways that are useful for the processing of that information. Okay, and what we are going to do is to define different ways of accessing the information, different recursive ways of accessing the information, and this is what we call traversals of the trees. Okay, so a traversal is a way of accessing the information that is stored in the nodes of the tree. Okay, and depending on the order in which we access this information, we are going to have different traversals. And we are going to study three different traversals, which are what we call the pre-order, the in-order, and the post-order traversals. Okay, and these are always recursive ways of visiting the different nodes in the tree, but they differ in the order in which we visit the different parts of the tree. Remember that in a binary tree we have three elements, which are the root, the left subtree, and the right subtree. So the order in which we visit these elements is what defines the kind of traversal that we have. Okay, so in all of them, what we do is to visit the elements stored in the nodes in order to do some operation with the information. Imagine that, for instance, you have integers, then what you can do is to try to find how many elements are bigger than 100. Okay, so you need to visit each of the nodes and count how many of them are bigger than 100. Or maybe what you have is information about clients of a company, and you want to find all the clients that live in Madrid. Then you have to visit the elements and compare the city in which the client lives to Madrid, okay? Or you want to store all the elements in a file, so you need to visit all the nodes and then write the information in a file, okay? So with visit, we mean any kind of operation that we want to do or that we have to do with the information that is stored in the nodes, okay? And that depends on the application, but what we are interested in here is the order in which we do these visits and how this affects the kind of result that we have, okay? So the first uh, type of traversal that we are going to study is what we call pre-order traversal. And the important part of the name here is pre, because what we are going to do is to visit first the element in the root, and then we go in order to the left and then to the right. Okay, so always with pre-order we first visit the root, then the left side, and then the right side. Okay, but notice that here we are doing a recursive call. So in this call and in this call, we are going to do exactly the same. That's why we have here this condition that if the tree is empty, remember that being empty is the base case of the recursive definition of the data structure. If the tree is empty, then we do not have to do anything, okay? Because there is no information there. So we have these recursive ways of traversing the tree, and anytime that we call the method again, we do exactly the same. Okay, we are going to have some examples of this kind of traversal in a few minutes, but first let me explain the different other traversals that we are going to study. So in pre-order, we first visit the root, then the left hand, the left subtree, then the right subtree. Okay. What about other types of traversal? The second type of traversal that we have is what we call in-order traversal. Again, the important thing here is in, and this specifies in which place we visit the root. So notice that the only difference with the previous definition is the order in which we have the visit to the root. In pre-order, we have the visit before visiting the left subtree or the right subtree. Here we have the visit in order in between the visit to the left and the visit to the right. Okay, so that's why we call this traversal in order, because it's in between both visits to the left and to the right. We first visit the left, then the root, and then the right. And as you can imagine, in post-order traversal, what we have is that the visit is the visit to the root is the last thing that we do. We first visit the left, then we visit the right, and then we visit the root. Okay, with visiting, as I've mentioned, we mean any kind of operation that we need to do with the information. Write it in a file, or sum up all the values, or put all the values to 0, or whatever. Okay, so we have these three types of traversal. The first one is pre-order. We first visit the root, then the left subtree, then the right subtree. Then we have in order, first the left subtree, then the root, then the right subtree. And finally we have post order, first the left, then the right, and then finally the visit to the root. Okay, so let me give you an example of these traversals with this tree here. Okay, so this is a binary tree, and we are going to do the three types of traversal that we have just defined. So let me write here. Let's start with the pre-order, okay, and see what is the result of this traversal. So in pre-order, remember that we first visit the root, then the left subtree, then the right subtree. So we start and we visit the root. So the first thing that we get is E. Okay? So this is the order in which we are visiting the different nodes. Then we go to the right, to the left, sorry. We go to the left. And in the left, we again are doing a pre-ordered traversal, okay? This is a recursive algorithm. So we do a pre-ordered traversal with this subtree. So then we first visit the root, and the root here is A. And now we go to the left. We have several different recursive calls still unresolved, but when we enter the recursive call, we need to first visit the root and then immediately go to the left. Okay, so we go here to the left and we visit the root, which is C. And now here we try to go to the left. But since the left subtree of C is empty, this call returns immediately. Okay, it checks that the tree is empty and then it returns. Okay, it does nothing and it returns. And now we need to go to the right. But with the right subtree of C, it happens exactly the same. We check that it is empty, we notice that it is empty, and we return immediately. Okay, so we were still here in this call to pre-order with this subtree. We have completed the call to the left subtree, and now we do the call to the right subtree of A. And here again we visit first the root, and then we try to go to the left, then we try to go to the right. But when we go to the left and to the right, we find that both trees are empty, so we return immediately. Okay, so oh, sorry, this is B here. Okay, so now we have completed this call here to the left part of the whole tree. So now we need to go to the right part. And in the right part, we first visit the root, this G here, and then we go to the left. When we go to the left, we visit J, and we know that we stop there because there is nothing to the left, nothing to the right. And then we go to the right part here. And in the right part, we first visit the root, then we visit the left subtree. We try to visit the left and the right subtrees of H, but they are empty, and then we go to D. And when we go to D, again we visit the right and left subtrees, left and first and then right, they are empty. We go back and we have finished all the calls that we had pending. Okay, so in this case, the result of a pre-order traversal of this tree is E, A, C, B, G, J, F, H, D. Okay, so let me try deleting all these lines here, and let's try to do the in order traversal of this tree. Okay, so what we do is now we visit first the left subtree, then the root, and finally the right subtree. So let's see if I have space here. Yeah, maybe. So in traversal. So now before visiting that root, I need to go to the left. Okay? And when I go to the left, before visiting the root of this subtree with root A, I go to the left. Okay? And now, before going to visiting the root of this subtree, I try to go to the left. But now the left here is empty. And then, now in this moment, I visit the root of this left subtree. I try to visit the right, it is empty. So I go back to the root, and now I visit the root. So this is A, let me write it clearly. Okay, and now I go to the right. In the right, I first try to go to the left, which is empty. Then I visit B, and then I go to the right, which is also empty. Okay, so now I have visited completely the subtree on the left. Now I visit the root, which is E. And now I visit the whole right subtree also in order. So for that, I need to go first to the left, so J, then to the root, so G, then I go to this right subtree, and in this right subtree, I go first to the left, H, then to the root, F, and then to the right, which is T. Okay, so notice that this is a quite different order of the nodes. I visit the nodes in a very different order. Okay, so the in order here is C, A, B, then E, then J, then G, then H, F, and D. Okay? Finally, let me erase all that. Finally, we are going to do the post-traversal of the tree. And to do that, we first visit the left subtree, then the right subtree, and finally, in the last moment, we visit the root. So let me write it here, because now I don't think I have space up there anymore. Okay, so we first go to the left. In the left, we first go to the left. Here we try to go to the left, it's empty. Then we go to the right. We leave the root for the last, and then we go to the root. But here the left part and the right part are both empty. Okay, so here we get C. Now we go to the right part, which is B. And then, only then, we go to the root. So we get CBA. Okay, now we have visited all the left subtree, so we go to the right subtree. And here we go first to the left, so J, then to the right, so we go to this subtree that has F as its root. And in this subtree, we go first to the left, so H, then to the right, D, then to the root, F. Okay, and now we have completed this left subtree, this right subtree. We can go to this root, which is J, and then we have completed both this subtree and this subtree. So we go to the root, which is E. So again, a different order when we do the post-order traversal of the tree. Okay, but the idea is always the same. We visit the trees and the root in some order, and we do that recursively. Okay, we are going to do some more examples, but I want to show you how this can be applied to an interesting case, a case that it's also related to the kind of algorithms and notions that we studied in the first 2 units of this course, because this can be used in order to evaluate the semantic value of arithmetic expressions or algebraic expressions, okay? Because when we have algebraic expressions involving binary operations, as for instance addition, multiplication, subtraction, division, powers, and all that, we can represent the information and the structure of the algebraic expressions, the arithmetical expressions, with binary trees. Okay, so for instance, here we have this expression 2 plus x minus 3 times y. We can represent this by focusing first in which is the weakest operation, the operation that we do in the last moment when we evaluate the expression. And here, because of the rules of of precedence between operators, and mainly because of the brackets that we have here, we know that the last operation that we need to compute is the subtraction. So that is the operation that we put at the root of the binary tree that is going to represent this this expression. Okay, and then we do the same with both parts of this subtraction. Okay, so we now focus, for instance, in 2 plus x, and here we have only one operation, so that is the root of the subtree, and its operators are 2 and x. Okay, and here it is important to notice that the order of the nodes is what node is the left child and what node is the right child. It begins to be very important, because for instance with the subtraction is not the same to have 5 minus 3 than 3 minus 5. Okay, so which element is the left child, which element is the right child, is important. Okay, so that's why we imposed this structure on the definition of the algebra of the binary trees. Okay, and then when we have this subtree complete, then we can go to this part here. Again, here we have only one operation, so that is going to be the root of the tree. Okay, and then we have the two elements 3 and 1. So this is why binary trees are important for us. One of the reasons, because we can use them to represent algebraic expressions. And when you get the parse tree of an algebraic expression, when you are performing a syntactical analysis, then you can construct this kind of binary tree in order to be able later to evaluate the expression. Okay, and how can we work with these binary trees for algebraic expressions? What we can do is to once that we have the binary tree, we can transform the expression into 3 different ways of representing the information of the algebraic expression, the structure of the algebraic expression. We can represent this in what we call infix, prefix, and postfix notations, okay, which of course have to do with the in order, pre-order, and post-order traversals that we have just studied. Because here what we are doing is, once that we have the binary tree representing the expression, if we do an in-order traversal of the tree, we obtain what we call infix notation. And the main property of this infix notation is that the operators are in between, the operations are in between the different parts of the operation. So, for instance, if we have an addition of 3 and 5, we have 3 plus 5. Okay, so the operator is between the two operands of the expression. Okay, this is the usual way in which we represent arithmetic expressions, and the formal name for this notation is infix notation, because the operation is inside, in between the operands. Okay. Another type of representation of these expressions is what we call postfix notation. This postfix notation is what we obtain when we have an expression in a binary tree and we do a post-order traversal. And here the operators are going to be after the operands. Okay, so here, for instance, when we have this plus is affecting this 12 here and this 6 here. Okay, it's affecting it's located after its operands. Okay, and this is also what is usually called reverse Polish notation. Okay, and this, for instance, is used in some scientific calculators. Okay, if you have used some advanced scientific calculators, you may have found this kind of notation in which the operands are introduced after the operations, or the operators are introduced after the operands. Okay. Finally, we have prefix notation, in which the operators go before the operands, because what we do here is to traverse the tree in pre-order. Okay, so the roots, which are the operators, are going to be before the operands. Okay, and this is also something that you have found, because this is similar to what you have when you have a notation in a programming language in which you have functions. Let me draw this a little bit better. So if you write here brackets and commas to separate the different arguments of the function, then you have exactly something that you can find in a programming language. If I define this to be the sum of 3 and the product of 5 and the sum of 6 and 12, this is exactly what you would find in a programming language. Okay, so when you define functions, functions are always in, or most of the times are in prefix notation. The name of the function goes before the arguments. Okay, so let's try to use these definitions in order to obtain the different notations in infix notation, prefix notation, and postfix notation of this graph here, of this binary tree. Okay, so let me go to the whiteboard and create a new whiteboard, or choose this one here, and let me copy the tree. Okay, so the tree was like this. Okay, and let's do first the in order traversal of this tree, and we should obtain the infix notation. That is the usual way in which we define, or in which we represent the arithmetical expression. Okay, so here In order to do the in fixed notation, the in order traversal, remember that we go first to the left, so 3, then to the root, so plus, and in order it's necessary to use brackets. Okay, so this is something that is not needed in the other types of traversals, but here in order to obtain, when we have an arithmetical expression, in order to obtain the correct in order in fixed notation, we need brackets. Okay, so here we go now to this left tree, and then we obtain, first we go to the left, so 5, then to the root, so times, and then brackets again. When we go to this right 3, we obtain first to the right 6, then plus, then 12. Okay, so this is the infix notation. Let me see if I can remove these lines. Okay. And then we try to do the post order traversal of this tree in order to obtain the postfix notation. Okay, so here we first go to the left, then to the right, so to this subtree here. And in this subtree, we first go to the left, so this part here, so 5. Then again to the right, so we go to this subtree here, and here we go to 6, then to the right 12, then to the root plus, then to this root times, and then to this root plus. Okay, so let me see if I can remove this. Well, I'm going to remove everything and copy the tree again. I think it's easier. Okay, so we now have the infix notation, the postfix notation, so we only need to compute the pre-order notation of this, the prefix notation of this expression. Okay, so 6 and 12. And for the pre-order, remember that we first visit the root, so plus, then we go to the left. Here we only have the root, so 3. Now we go to the right, and here we first visit the root, so times, then we go to the right, to the left, so 5, then we go to the right, and there we first visit the root, then the left, and then the right. Okay, so this is these are the 3 different notations for this expression, and you can obtain them, as you can see, as you have seen, with the different 3 traversals that we can do in this graph. Okay. Another thing that is interesting about these 3 traversals and these notations is that we can go from some of them, from one of them to the other, to other of them, or to evaluate them in a very quick way. Okay, so for instance, if we have the post order notation, it is very easy to evaluate the value of the expression. Okay, so let me give you the example here. Let me copy again the post order notation for this expression, and let's see how to evaluate the value of this expression once that we know the pre-order, the post order notation of the expression. So what we need here is a stack. Okay, we are going to use a stack to evaluate the value of the expression. And what we do is to apply two rules. The first rule is that when we find an operand, we push that operand in the stack. Okay? And when we find an operator, we read the expression from left to right, and when we find an operator, we pop back two elements from the stack, we compute the result of the operation with those two elements, and we pop back the result in the stack. Okay, so two rules. If we find an operand, we push the operand in the stack. If we find, second rule, if we find an operator, we pop back two elements from the stack, we compute the result of those two elements with the operation, and we pop back the result to the stack. So here what we would have would be 3, which is an operand, so we push it into the stack. Then 5, then 6, then 12. Okay, so we have found operands, so we push them in the stack. Now we find the first operator, which is plus. So we pop 6 and 12, and we compute the result of the operation, in this case addition, with 6 and 2. We leave the rest of the stack as it is, and then we add 6 and 12, and we obtain 18. Okay? Now we find another operation, which is a multiplication. Okay? And then we pop back the two elements that are at the top of the stack, in this case 5 and 18, and we compute the operation. So 5 times 18 is 90. So we pop back 90 to the stack. Okay? Finally, we find an operation, which is in this case an addition. So we pop back the 3 and the 90, and we compute the operation, and we push it back to the stack. Okay, so in this case we have finished, and we have the result of the operation of the whole expression in the stack. Okay, so that's why this is interesting and this is useful. Okay, so let's do another example in which we have an expression, and then we compute the infix notation, the pre-order notation, the prefix notation, the postfix notation, and then we evaluate the expression with this algorithm. Okay, so let's say that is 7 plus 2 times 5 minus 1 plus 2. Okay, so in this case, the last operation that we need to perform is, of course, the multiplication, and then we have an addition of 3 and 2. Okay, then we have here a subtraction of 5 and the addition of 1 and 2. Okay, so this is the order, the tree of the expression. Now let's compute the in order traversal of this tree, so we can obtain the infix notation. Okay, so we go to the left, and in the left here we first visit the left part, then the root, then the right part. So we obtain 3 plus 2. And remember to use brackets when you are computing the in order notation. Okay, then the root, and then we go to this subtree here. Okay, so in that subtree, first the left part, which is 5, then the root, which is the subtraction, and then we go to the right part. And in the right part, first the 1, then the root, then the 2, which is after right. And we, of course, obtain the same expression that we had at the beginning. Okay? If we do the pre-order notation, we obtain first the root, then the root of the left subtree, then the 3, then the 2, then the root of the right subtree, then the left part, then the root of the right subtree, then the 1, and then the 2. Okay? Finally, to obtain the post order or traversal, to obtain the postfix notation, what we do is to first go to the left. In the left, we go to the left. And here we have no more lefts to go, so 3, then the 2, then the plus. Okay, then we go to the right. And in the right, we first go to the left. 5, then to the right. So in the right, we go first to the left. 1, then 2, then plus. And then the root, and then the main root of the tree. So this is the post-order notation. Okay, and from this post-order notation, let's evaluate the result of this expression. And to do that, remember that we need to use a stack with the different elements that we are finding in the expression, in the notation of the expression when we read from left to 2. So 3, then 2, then we find a plus. Okay, so in this case, we pop back both elements and we obtain as a result 3 plus 2, which is 5. Okay, now another 5, now another 1, now another operand, which is a 2. Okay, let me erase this here. So here we had found the plus. Now we find another plus and we substitute here 5, 5, the 1 and 2 with 3, which is the result of 1 plus 2. Then the subtraction. So here we substitute 5 and 3 with 5 minus 3, which is 2. And finally, the multiplication, and we obtain the result, which is 10. Okay, so this may seem over complicated for evaluating an expression that you know how to do because you have studied arithmetic expressions for many years. But this is a very useful way to teach the computer how to evaluate this, because you only need 2 simple rules to push operands into the stack, to pop back operands in order to compute the result of operations, and you only need a stack, which is something that is in any computer. Okay, you have this structure at your disposal in the computer. Okay, so if you have an arithmetic expression, it's usually very easy to evaluate the expression in this way. Okay, and with this we have completed the lecture on trees. Remember that on Friday we are going to have a live session through Microsoft Teams, and we are going to solve different exercises from the worksheet. Okay, if you have any question, please email me or leave a comment on the discussion forum. And thank you for your attention as always.